Okay, we good to go? Okay, I think we're going to get started. Thank you everybody for coming out. My name is Michael Armbrust, and I am the lead developer of Spark SQL. I work at Databricks, and I'm going to be this is kind of a developer-oriented meetup, and I'm going to be telling you all about Spark SQL and some cool new APIs that we're adding specifically for developers who want to contribute to the project. So just kind of a high-level overview of what I'm going to be talking about. I'm going to kind of give a brief overview of Spark SQL for those of you who aren't super familiar with it. But kind of, in general, this is kind of going to be some of the lower level details. I'm going to talk about writing a rule. So Spark SQL's optimizer is actually based on these relatively simple rules, all of which come together to make query optimization happen. So I'm going to show kind of what rules are and how you write them. I'm going to then kind of walk through the actual steps of query optimization, how we take a SQL query that you give us and we turn it into a Spark plan that can run as efficiently as possible. I'm also going to then kind of go into some of our new data sources and talk about how you can add them, add new data sources to Spark SQL using this API that we're adding for Spark 1.2. I'm going to do an overview of what it means to contribute, how to make a pull request, and then I'll have some time for questions. And really, this is a pretty informal talk. This is geared towards developers, like I said, so please feel free to interrupt me. If at any point the code isn't clear or whatever, I'm happy to answer questions as we go along. So one thing I'll say is, you may have noticed I'm not using PowerPoint here. I'm actually presenting inside of Databricks Cloud. And what this is it's basically an interactive notebook environment inside of the browser. It lets you write code in Scala, Python, or SQL and kind of execute it right away. And it then runs that on Spark clusters of arbitrary sizes. So we're currently in limited beta, so you can't try this out just yet. But we'll be rolling out more widely soon. And until then, kind of one of the where we feel very strongly about it is the importance of the open source Apache part of Spark. And so all of the examples from this talk will also work in a standard Spark shell on your laptop. Another thing I'll tell you about, if you don't know about it, if you're looking to contribute to Spark SQL, in addition to the Spark shell, there's also this thing called the Hive console, which is great for debugging code that you're working on. Basically, all you do is you do SBT Hive console, as it shows here at the bottom of the screen. And it'll bring up a Scala interpreter with all of the Spark SQL libraries loaded in, and it even test instance of Spark SQL with Hive in that single JVM with test data and stuff. So you can see in this example at the very bottom of the screen, we're saying like select star from SRC. Well, SRC is a test table. So there's actually a bunch of test tables you can query right away. So if you're adding features in, it's a great way to kind of quickly iterate and test things out. So, why would you want to contribute to Spark? That's, maybe a first good question. And, it turns out in the last release alone, we had over 175 people contribute to the Spark project. And, we feel pretty strongly that actually one of the things that makes Spark really awesome is the kind of community involvement. It's not really just us at Databricks writing code. In fact, these days I spend more of my time reviewing patches from the outside than I do writing code myself. And, the level of involvement from people in the community has been only increasing as we go forward. So this is a chart starting with release 0.6 way back when it was mostly people in the AMP lab. Each release, it just continues to increase significantly, the number of people that are. If you want to kind of join in and participate in this cool open source community, that's kind of what this talk is geared for. So let's dive into Spark SQL now. So first of all, what is Spark SQL? Well, it's of Spark. It's a very young project. It's only been around for less than a year. I think I actually started writing it last October, so we're coming up on the first birthday of the first commit. But in spite of its relatively young age, it's actually already had over 60 contributors to just the SQL part of the project. And we've added all kinds of things. I'll be talking about some specific examples through the talk. But the key idea here is, RDDs are great. It's a great way to do distributed transformations, but sometimes you want a higher level language. And that's basically what Spark SQL does. It's not doing anything you couldn't do with RDDs by yourself. In fact, every operation Spark SQL does compiles down into an RDD operation. It's all map and map partitions and collects and things like that. But we do that automatically. You relatively simple SQL specification of the job you want to run, and we find the most optimal way to run that on top of Spark, doing kinds of all sorts of optimizations throughout the way. A question we get pretty often is, how does this relate to Shark? Is this the same as Shark? Is this different as Shark? What happened to Shark? I can say is, the goal is very similar. For those of you who aren't familiar, Shark was a project also started at the AMP lab where it basically took the Apache Hive optimizer and query planner and replaced the back with Spark instead of MapReduce. So instead of running your Hive jobs as long MapReduce, you could actually compile them down to interactive Spark jobs that would take advantage of data stored in memory. And so this was great because it gave you, in some cases, up to 100x speed up over existing Hive installations on the same hardware. But the problem here for us as the developers was it was very difficult for us to add features. When we found something where the Hive optimizer wasn't doing what we wanted it to do, it was quite a bit of work to change it, to get it to kind of behave better, align more closely with Spark's execution model. And so the entire goal of Spark SQL and Catalyst, which is the name of the optimizer for Spark SQL, was to build a modular framework for optimizing SQL queries that was designed specifically for the Spark execution engine. And so, while the goals are very similar and we're pretty close to feature parity with Shark, I would say most people I know who are using, many people I know were using Shark have now transitioned to Spark SQL. This is actually a pretty from scratch rewrite. In addition to Hive, though, Spark SQL is actually quite a bit more than that. So we do support reading data that's stored in Hive and the Hive metastore using Hive SERDES and Hive UDFs and Hive QL. But we also support reading data from Parquet, JSON, and other data sources. And I'll be talking about some of those other data sources as we go through the talk. So I think an important question here is, what is the key difference between working in Spark and working in Spark SQL? And really important is the kind of notion of a schema RDD. So with Spark, what expressing these functional transformations on these collections of opaque objects that are spread throughout a cluster. So I say map, and Spark makes sure that map gets applied to each of these partitions throughout the cluster kind of automatically and takes care of all the fault tolerance for me. But a key thing to realize is Spark has no idea what's going on inside of your map function, and it has no idea what your data actually looks like. So it could be that you're actually only touching a small fragment of that data. And since Spark doesn't know that, it's up to you as the program writer to put all of those optimizations in yourself. With Spark SQL, instead, we've added schema to our collections of data. And what I mean by schema is we actually know the names of the columns. We know their data types. We can do more efficient things like when you cache a table with Spark SQL compared to caching an RDD, we actually do compression. So we'll take advantage of the fact that the age column is an integer and most ages fall within a relatively small range. We'll detect that automatically, and we'll do efficient delta encoding, which is something you wouldn't get if you were using Java serialization or even Cryo. There are significant advantages to adding schema. And then another thing that's actually pretty important is that instead of writing these kind of imperative programs where you're saying exactly what should be done and in what order, you're giving it a declarative specification of the problem. So when you write a SQL query, you're not saying how to retrieve the data. You're saying only what data you want to retrieve. And then it's up to the optimizer to figure out the way to actually execute that query. And so there's quite a few benefits to this. So the nice thing to realize is forth between schema RDDs, and schema RDDs are still RDDs. So you can RDD operations on them. So if there are things that don't fit nicely inside of SQL, you can easily drop back into Scala, Java, or Python. So now let's talk a little bit about how to actually create a schema RDD. So I'm going to start in Scala. And basically, the way you create a schema RDD in Scala is you create a case class. So a case class is this relatively simple construct. It's kind of similar to a Java bean or maybe a name struct in Python. But the idea is, with a case class, all of the arguments to the constructor are also public members of that class. So you get all of the getters written for you automatically by the Scala compiler. And the way to think about this is each of the fields to the constructor of this person class is like a column in a traditional table. So I'm saying, I want to create this type of data called person. It's going to have two columns, name and age, and they're of type string and integer. And so in this example here, what I've done is I've created this class, and then I'm using standard Spark to create a parallel collection containing these items. So this is the parallelized person. I'm passing it a list of people. And basically, any RDD that contains case classes, as long as there's a SQL context in scope, can automatically a schema RDD. So there is no register temp table operation on a normal RDD. And we'll figure that out. And so what it'll do is at compile time, it'll actually go and figure out the schema of the data and kind of tell Spark SQL about that and turn it into RDD automatically. So when I run this command here, you can see it's now basically defined this new class. And now I've got a table called Scala people. So what I can do now that I've done this is I can run kind of standard SQL queries. So if I run this SQL query here, you'll see it's going to return something that is of type schema RDD. I can see the query plan is just take this existing RDD and pull out the data that is of type name and age. I'll go more into how to read these query plans later in the talk. Since it's a normal RDD, I can do all of the standard operations. If I want to actually retrieve the data back to the driver, I'll do a collect. And you can see it retrieves back a row that contains 2 columns, Michael and 30. And the kind of cool thing here is now, so SQL is great. There's a lot of things SQL is very good at. But as I said, sometimes there are constructs that are difficult to express in SQL. It's much easier to express them in Scala. And so you can take the results of your SQL query and drop right back into your Lambda functions. So in this case, I'm running a SQL query that pulls out only the name column. And then I'm running this Lambda function, which takes the first column and does some kind of string manipulation with it.
Can we store it in another table?
Yes. So from a schema RDD, so this is also a of a SQL query is also a schema RDD. So you could do something like so if I wanted to do something like this, I could do name and then register temp table names, right? And now I can actually query that. Oh, I guess name is what I called it, typo. So you can see you can query that, and then it'll actually give you what you actually want. So so one thing you can do, view schema RDDs as traditional database views. You can build up kind of relatively complex queries in parts. And what you understand is the optimization is not done until you perform an action. So until I call collect, all we're keeping around is the logical structure of the query, holistic optimization of the entire query when you actually call the operation. So there's no downside to composing your SQL query in parts, registering it temp tables, and kind of then combining it together. Any other questions before I move on?
Need to fit like master or OneNote, right? So this collect can distribute.
No, collect in particular is a special operation. Anytime you run a collect, it's going to retrieve all of the data back to the driver. So if you did not want to do that, if it was too large to fit in the memory of the driver, you should do save as Parquet file or save as text file or some distributed operation, like write it out to a distributed storage system in parallel. But collect on normal RDDs or schema RDDs requires the data will fit in memory.
If I want to manipulate co-located data, then collect might be the way to go.
Yeah, I mean, if you need to get it back, then yes, collect is the right thing to do.
Have you moved to using macros from reflection?
Yeah, yes, that's a whole nother talk. But yeah, so basically we've got this. Turn on, it's Spark SQL.CodeGen. And if you turn on Spark SQL CodeGen, we use runtime reflection to build up basically Scala bytecode or Java bytecode to expression evaluation. So and it uses library to do that.
Right, but you were talking previously, I've talked to you before about converting case class stuff to macros. Is that all done?
No. Oh, so, okay. Yes. Okay. Now I remember this question. It's not done. There is a pull request, a work in progress pull request called type SQL on GitHub, which does it. So there is a library that does that. It is not merged into master yet, and it still needs some work. But actually, if you're interested in that, you should totally check it out. I'd love to talk about any bugs you hit with it. But we've been working closely with EPFL to do that. Basically, what the question here was, is it possible to back from the results of SQL queries to case classes? And the answer is there's a very experimental patch that uses all sorts of Scala math possible, but it's not yet. And we're hoping to get an experimental version of it in for 1.2.
Is the forwards in?
The
forwards used to be runtime reflection also. It was like it came up to a thread safety offer.
Oh yeah, no, that's not in yet either. Yeah, yeah. Sorry, for type tags, that's actually still that's still at runtime.
If you apply the map to the case class, where you want to convert the type, you won't automatically do that.
So if you applied a map to the RDD of case classes, that's a normal RDD operation. So a conversion would have never happened, and you would just get the case classes back. Cool. So I'm gonna move along, but please keep asking me questions as we go. So real quick, I want to point out you can do all of these things not only in Scala, but you can also do them in Python. So here's a very similar example. In this case, basically what I'm creating a collection of row objects. Row is a special Spark SQL thing that we've imported from PySpark SQL. And here you're using key. So the name of the column equals the value. Since Python is not statically typed and SQL expects us to have types for everything, basically what you're going to do is you're going to run this command called infer schema. And that's going to take the first data item in your collection and use that to guess the schema. One of the things we're working on doing is doing kind of more thorough schema entrance based on all of the data. That's also something that's not. So basically, same thing. I took this, I registered it as a table, and now that I've done that, I can run Python Lambda functions on it as well. Cool. So in addition to working with kind of standard relational data, one of the cool things with SQL is we've also got the ability to work with semi-structured data. So in this example, I've taken a bunch of tweets stored as JSON directly from the Twitter fire hose. And what I can do is I can actually just kind of point Spark SQL at them. And what it did is when I hit enter, it went out, it launched a Spark job, and it read all of those tweets and figured out every field in the JSON that exists in any single one of the tweets and unions all of those schemas together to give you kind of a global schema for all of the tweets that exist. And it does kind of fairly intelligent things. If you have an integer and a long, it promotes it to a long. If you have an integer and a string, it just becomes a string. So as long as your kind of JSON has a relatively reasonable structure, we're actually able to infer it kind of automatically. And then if it doesn't get it right, you can always write SQL queries to convert it to the form you actually want. So in this case, you can see I can do tweets and print schema. And this will actually give us kind of a full view of the schema. You can see Twitter has a relatively complicated nested schema. This is actually Spark SQL is kind of not purely relational. It's not for like MySQL, for example, and it does support nested structures, which you can kind of dot into, and also arrays and other things within your data, kind of similar to what Hive does. And so once I've done that, I can now write select text from tweets. And so that brought back a whole bunch of tweets into my console.
You're not using the Spark SQL context, you're using the Hive SQL context, right?
Yes, so all of these examples are run with a Hive context, just because I wanted to also include Hive examples. So this is actually a very good distinction to be made. There's two types of SQL context right now, and really the only reason for this is because we didn't want to include all of Hive's dependencies in the standard Spark distribution. We're afraid it was going to break existing applications. So there's a SQL context, which allows you to do very simple SQL, and there's a Hive context, which allows you to do HQL and also access Hive tables and things. In general, if you can, I strongly recommend you use the Hive because the Hive QL parser is significantly more complete than the SQL parser, and the Hive context can do everything the SQL context can do. The only reason to not use a Hive context is if you can't deal with those dependencies. There's some conflict with an existing library you're starting to get, basically JVM exceptions saying libraries can't be linked.
But if you're starting from scratch, then you should be good.
Yeah, I would recommend starting next in that case.
When you mentioned the nested data, have you gotten the nested column stores in memory working?
So it does work. It is, I would say it's not going to be as fast as Parquet, for example, because the way it's going to work is so you can store nested data in columnar.
Serialized as bigger blobs.
It is still serialized as bigger blobs. So it's still not going to be as efficient as Parquet. I believe when you asked this question last, there was a horrible bug where we were creating a new instance of cryo for every single tuple, and so it was really slow, and it's now pretty fast. Yeah. Oh, okay. Oh, good.
It's still hard to slow.
Okay, yeah, no. I mean, honestly, if you've got complex nested data, Parquet is our answer. And that's kind of what we're going to push people towards. And if you want to take complex nested data and put it in memory, Parquet on Tachyon is kind of what we're thinking is the best option. Because to do it efficiently, you're going to end up reinventing something like repetition and definition levels. And we kind of don't see any need in doing that when there's already a pretty decent format.
But does Parquet have this notion of tables and appending to those tables, which are already there, instead of like appending to files?
No, so you can add new Parquet files to a directory. You cannot append to existing Parquet files. You can also not append to existing column buffers. So I would say they're pretty similar in this regard. So, OK, great. Thanks for all the questions so far. So that was kind of the overview of kind of the user side of Spark SQL. What I want to do now is I want to dive into some of the deeper APIs. And before I do that, I want to talk a little bit about Spark's API annotations. So one of the things we take very seriously on the Spark project is kind of making sure that people who write applications against Spark will always be able to run those applications, even as we evolve the project. So we've made a commitment to be at least source compatible and most likely binary compatible throughout the 1.x release for all of Spark Core. So if you write something just against Spark Core, you should not even have to recompile your applications. In Spark SQL, we're an alpha component, so we don't make exactly the same promise since it's so young. But I try very, very hard to make sure we're at least source compatible, and we don't break binary compatibility unless we absolutely have to. That's kind of generally the case for everything. We want to be a stable platform for people to build upon, but because we also want to be able to, as developers, continue to make things better. We don't want to be stuck with design decisions from years ago that no longer make any sense. What we've come up with is a set of API annotations. So basically, anything in the Spark Core public API should be stable, unless it's annotated with one of these two annotations. So there's both developer API and experimental. So developer API means, once again, we're not going to try to change it for no reason, but this is considered an internal detail of the system, and we may change it if we have to. So examples here are like the progress reporting from a job. If you want to hook in very deeply and get that information back, we may change those APIs. But if you're just doing .maps and collects and save as text files, all of those will work forever. Another example annotation is experimental. These are features where we haven't fully vetted them. We're not sure if it's like a perfect idea yet, but we might as well put it out there so people can use it. So once again, we may change them in minor versions, or they may get promoted to be full first-class APIs if a lot of people use them and we decide we like them. So everything that I show you after this talk, it should be considered a developer API. So it'll be there and it'll be stable, but not the same promises. So one of these things is the query execution. So I showed you before the idea of looking at the query plan. When we printed out the schema RDD, you could see the physical plan. But that's kind of only one part of the story. So let's start with a kind of artificial schema and an artificial query. In this case, I'm creating a table called people. I have a page. And I'm also going to add one other thing to this table. We're going to add a partitioning column called state. So just a quick explanation of what a partitioning column is for those of you who are not super familiar with Hive. The idea here is this actually dictates how the data is stored. So there's one folder for California, there's another folder for Illinois, and if I run a query where it says, select star from people where state equals California, it'll only read from the California folder and skip all of the other data. So this is a huge performance optimization. And we're kind of telling the database that we're often going to be running queries where there are predicates on the state. So what I've got now is I'm going to run this query. This is basically, it's a complex way to say, show me all the people who live in California. I'll go through, this is a kind of a purposefully complex query, because Spark SQL is going to figure out how to make it simple as we go along. And you can see in this case, what Spark SQL does is it condenses all of that SQL down into a single operator, a Hive table scan, that pulls out the name column. And then at the very end of that last line, you can see state equals California. And so that's saying that that's a partitioning column, and we're only going to read from those partitions where that is true.
But if it becomes a hot partition,
I'm sorry?
if it becomes like a hot partition, so everybody's like querying California, then...
Well, so actually, that's not necessarily a problem as long as you have HDFS replication high enough, so those blocks are available on multiple machines. But yeah, that could become a problem. So But that's the end of the story. The question is, how did we get there? And if something broke, how do I fix it? So the query execution is actually a way to dive in and look at kind of the details of what's going on. So call .query execution on any schema RDD, and you can see now it's actually giving us three or four different plans. The plan straight as it comes out of the Hive parser, the plan after we've analyzed it and figured out all the data types, and the optimized plan. And then finally, the way it's actually going to be executed. That's the physical plan on the bottom. And so this is kind of relatively low-level developer details, but when something breaks, this is a great way to figure out where it broke, why things aren't working. And you can actually pull out each of these phases kind of individually by name, so I can pull out the analyzed plan, or I can also pull out the optimized plan. So, OK, why would you want to do that? Why would you want to see these query plans? And another question is, what were all of those weird numbers that were showing up? So you may have noticed that kind of all of the attribute names were prefixed by these weird numbers. And the reason for that is Spark SQL actually kind of does this on purpose. We assign these globally unique IDs to attributes. And that's so that we can track data flow throughout the plan, even when there's ambiguity. And we can do all the optimizations we want, rearranging things, and not worry about forgetting where things are coming from. So for example, we can delete subqueries and still know where data is coming from. So in this example, I'm actually joining a table with itself. So I'm joining the people table with itself. And what you'll see is that in the condition here, it's actually on state equals state, but I can tell which state it is based on that number.
You have the lineage, right?
Yeah, exactly. This is the lineage of that attribute through the query plan. So just kind of an important thing to realize about attribute references, that any instance of a relation will have a unique attribute ID. Now that you know that, let's start writing a rule. So rules are these ways to transform trees. Almost the entire Spark SQL optimizer is written as rules. And what you can do with rules is you can basically take things and you can express patterns that you want to turn into other patterns. So let's start with a relatively simple example. In this case, and there are trees all throughout Spark SQL. Logical plans are trees, and expressions are trees. So in this case, let's start with a really simple expression. I've created a tree that adds 1 and 2 and then multiplies it by 3. So I constructed it here. You can see here is the actual expression. But let's say I want to do kind of a relatively arbitrary transformation. I want to turn it into subtraction instead. So what I can do is, I'm going to say operation. So this is the tree I want to do a manipulation on. Transform. This is a function that's available on all trees. And the argument to transform is a partial function. So I pass it a function that only applies to some trees. And when it doesn't apply, Spark SQL is going to just skip over trees that it doesn't apply to and only make these changes where it does apply. So I'm going to say case, and I'm looking for an add operator. We'll say it adds A and B. And I want to change it to subtract A and B. And so you can see what this did is, because this function is only defined on add, it just skipped over multiply and left multiply as it was. But because it was defined on add, it switched the addition to a subtraction. So you can see here, we now have a subtraction instead of an addition. So that's kind of silly. Yeah, question? So this is all Scala. So unfortunately, the developer APIs for writing the optimizer probably will only ever be available in Scala, because this is not something user to do, but somebody who is trying to make Spark SQL faster. Although we are looking at doing some of the kind of query DSL stuff in Python, but that's like a work in progress.
In general, can you only write rules using the catalyst expression?
Yes. Yeah.
And
Yep. Exactly. Yeah. This is all kind of internal details that we would kind of only expect, kind of developers of Spark to do. So now that we've seen kind of a simple manipulation of expressions, let's try to do the same thing with a query where it actually makes a little bit more sense. I've written this kind of arbitrary query where I take people and I filter it by two different things. So I'm going to filter it on name and I'm going to filter on state. But it seems kind of silly to have two filters when I could have just one filter with an and instead. That would kind of be more efficient. We'd avoid an extra virtual function call probably. So what I'm going to do now is I'm going to write a rule to do this. So you'll see I've got this filters. It extends rule. Basically what this is the way we actually plug this into the optimizer. The optimizer is just a collection of these objects that inherit from this rule class. And it's a rule on logical plans, which means it takes in a logical plan and it produces a logical plan. And in general, the rule should be you take in a correct plan, you make a relatively small change, and you return a correct plan that returns the same, but hopefully a little bit faster. So in this case, we'll do transform. And we're going to look for cases where there are two filters each other. So filter, and we'll say condition 1, filter and condition 2, and then the grandchild. So we're matching on this pattern, and we're pulling out the individual conditions from the filters that we're finding into C1 and C2. And we want to replace that with a single filter where conditions 1 and conditions 2 have been ANDed. And then we'll just plug the grandchild right back in as well. So now we've defined combined filters. Can run combined filters on that original query. And you can see, ta-da, it has replaced the double filters with a single filter. So great, OK, that's pretty cool, but that's pretty simple. How do I actually take a really complicated query and turn it into something that I can execute using these simple rules? So one great example here is this relatively recent case, I think, from the Spark mailing list. Basically, somebody emailed the dev list, and they're like, my Parquet query with unions is running way slower than it should be. Why is that? They included the query plan. I said, oh, yeah, we're doing something wrong. We should be pushing filters down to either side of the union, right? If we know we're going to filter something, we should filter all of the things that we're unioning together. And so this person who had never added anything to Spark came in, wrote 110 lines of code. More than half of those were tests, actually. And they committed into Spark. Within a week, people were already emailing the dev list saying they had some job, it used to take forever, and then crash in the end, and it now runs in 200 seconds. So basically, by just adding 50 lines of code to Spark SQL, they were able to make their workload run significantly faster in any case where you ever union multiple Parquet files together. So I thought that was a pretty cool example of contributions making the project better. So now let's actually dive into a slightly more complicated example. I want to show the entire execution flow of this query and how we do it using rules. So once again, we're gonna start with this pretty complicated query here. And what you can see, we're going to start with this thing called an unresolved relation. So this just means we've got some table. It's called people. I have no idea where it's coming from or what it's going to give us. We've got this kind of silly filter that says, does 1 equal 1? But actually, the data types are wrong here. 1 is an integer and 1 is a string in various cases. We've got this project where we're pulling out the name and the state, and we're renaming the state to be location. We're aliasing everything with a subquery, so now it's called A instead of people. Filtering on the location, which is that thing we just renamed. And then finally, we're projecting out a.name. So this is basically what Spark SQL gets from Hive. We still use the Hive parser, and this is what the Hive parser gives us. How do we actually execute this? So step number 1 is called resolving relations. And what that does is it actually goes to the Hive. It basically finds it's a rule that finds any unresolved relation. Anytime we find one, it goes to the catalog and asks for it. So this is pretty simple. All we did was we took the unresolved relation. We said, oh, I found a copy of people in the meta store. That must be what they're talking about. So now we know where the table's. The next step is now that we've got the table, let's figure out what all of the attributes throughout the query plan are referring to. So in this case, you can see beforehand, all of the attributes have these little ticks next to them. Ticks mean that they're unresolved. We don't know where they're coming from yet. And afterwards, they all have these globally unique expression IDs. So we now know the data type and kind of provenance of every single data item throughout this query plan. Yes? Oh, it's to the JVM, to the running JVM. So these are allocated with an atomic long. So it is not safe to do optimization in one JVM and then mix it with trees from another JVM. And so actually, this is a thing that you need to be fairly careful about when you're working on the execution engine. All query planning should be done on the driver. And then the executors can only run those expressions. Yeah, very, very good question. So now we've got the data types throughout. And basically all this rule does is says, find any node where there's an unresolved expression and where the child is resolved, and then see if any of the things I'm looking for exist in my child. And so what ends up happening is the expressions just bubble up throughout the tree. So you actually kind of figure out the data types as it bubbles up as we go through. So now the next thing is we've got that weird cast where the types don't match up. So what Hive does in this case is anytime you try to do anything with a string and a number, it turns that scalable. So we handle that through the promote strings rule. The nice thing here is since this is a separate rule, we can actually flip on this thing, this on and off. So if you want to have MySQL semantics and not do that, you can turn this rule off. And if you want Hive semantics, you can include this rule. So basically what it does is it found this case and it adds this cast. So now the string is being turned into a double type. So the conversion now makes sense. And so then the final thing is now that we've figured out all the data types, everything's been cast correctly, we can eliminate that subquery. So it doesn't matter that we alias that table anymore as A because we figured out all of the names throughout. And the subquery is kind of just getting in the way of other optimizations. Anytime you can, you want to remove operators or collapse operators to make things simpler. That'll make it easier for us to find patterns that we recognize later on. So we remove the subquery, and now the next thing we'll do is called constant folding. And one thing I should say is basically what I'm doing in this demo is I just pulled the functions out of the actual SQL context using reflection, and I'm just applying them to the actual time. So basically what this rule is going to do is going to find any expressions in the tree that can be evaluated statically or constant folded without knowing the data. So 1 = 1 is always true no matter what data you give me. So in this rule, we convert this to, instead of being 1 = 1 into true. So OK, that's cool. We're getting closer. Things are getting simpler. So the next step is that filter is kind of silly. Why would you ever have a filter true? So we have another rule called simplify filters. And it basically does two things. It either removes filters that are true or just cuts off entire trees where you filter false. So if you've got a filter that statically evaluates to false, there's no need to read any data. I can just return 0 rows. And so kind of that's what this rule does. OK, so this is getting quite a bit simpler. We've gotten rid of a lot of the cruft. The last thing is this filter is pretty high up. A pretty standard trick in databases is to always try to push your filters down as close to the data source as possible, because that way you're filtering out data early and you don't have to do extra processing on it. So this rule is called push predicate through project. So it finds any case where there's a filter on top of a project and tries to push it through. So we can run that. And you can see it did kind of two things. Those operators have now rearranged themselves here. And this is now on state instead of location. So it actually kind of wrote through the alias, substituting in any expressions that were defined inside of that projection. So now kind of the final thing that's maybe a little weird about this query is we're doing 2 projects in a row. That seems kind of redundant. We don't even need the state column. So maybe we can get rid of that. So we've got this other rule called column pruning that basically tries to eliminate unused columns wherever they exist throughout the plan. And at the end of that, we've actually got a pretty simple query. So it's take this table, filter out the things where the people aren't from the state, and then project out their name. And so this is the end of optimization. So we analyzed it to figure out all the data types. We optimized it to get it down to a much simpler, more efficient plan. And now we actually need to plan it. We need to figure out what operators are we actually going to run, what RDD operations are we going to call. And so in this case, we call the query planner. And the query planner has a bunch of rules that say, recognize these various patterns of logical plans and try and execute them. So one pattern we've got is Hive tables, where there's a predicate that's on a partitioning column where you're then asking for some subset of the attributes. And so the final step here is to realize that we can apply that pattern to all of the operators here and turn this into a single Hive table scan where we prune early on the partitions. And then I made a mistake, and there's actually no data in this table, but I can run this query, and it will return nothing. But it didn't throw an error. So that is actually, this is exactly what happens when you run a query in Spark SQL. A couple of differences. There's actually a bunch more rules than what I showed you. I took the minimum subset of rules to get this specific query to compile down. And another trick that we do is we actually run most of these rules to fixed point. So sometimes the rules bounce off of each other, kind of actually doing something very complicated. So you may constant fold part of an expression and then realize that the other part is null, which allows you to do folding, which allows you to turn it into a true, which allows you to prune the filter. And so what we do is we actually kind of run all of these rules over and over again until the plan stops changing. Yeah? Yeah, so you have to, you could. That is totally possible, and there's nothing in the transformation framework that prevents you from doing that. Part of writing rules in general is that they're idempotent, so they won't just keep running forever, and that you don't have two rules back to back that kind of undo each other. And so one of the things we do for this is we have batches of rules that run to fixed point. We don't run the entire optimization pipeline to fixed point. But that is a problem. You have to think about it when you write rules in order to prevent that. Cool. So okay. So yes. Expand a tree. Oh yeah, totally. I mean, rules can do anything. I'm trying to think of a case where you'd want to expand. So in one example, what we do is I don't know if this is really expanding, but we do have a rule, for example, that finds cases where you're reading a table from Hive that's stored with Parquet, using the Parquet SERDI, and we switch it to instead use our own version of Parquet, and we insert some other operators on top. And so that does kind of expand the plan. So yeah, you can do whatever. Basically, the only rule is I match some pattern and I replace it with some other pattern of tree. And then it's kind of up to you as the optimizer designer to be clever about what rules you write to actually make the query faster. Yes?
How do you decide the order to apply for the rules?
Yeah, no, that's a very good question. It's basically there's like a lot of database literature on this, and so we're kind of reading a lot of the database papers and doing the things they're doing. That said, it's not always easy. Reasoning about how to do it. I mean, and so if you're, I guess, kind of the question is like, how would you do this? Often what happens is somebody presents something on the dev list or on a Jira about something they would like to do, and then we talk back and forth about what the right pattern is to match on, so that you aren't going to run into any of these cycles or other cases, and in which phase of optimization it should go. But honestly, it's kind of almost a matter of taste. Like after you've written enough of them, you start to reason about, that makes sense to put in analysis, or that belongs in expression optimization, or kind of things like that. Yes?
What's the status of the expander support? I know Jump is writing something, DataStax has written a driver for Spark. So is this like a separate driver that Databricks is independently working on?
Yeah, notice, okay, let me by that. So there are a couple of libraries that interoperate with Cassandra. They interoperate with Spark SQL to varying degrees. We have been talking with DataStax in particular, but also the TupleJump people, about working with these new APIs. Databricks in particular is not working on a Cassandra connector. Our goal is to make a public API for Spark SQL that allows anybody, including DataStax and other people who want to plug deeply into the optimizer to take advantage of some of the optimizations we're talking about, while integrating closely with data source X. Where
this might be a question I could ask afterwards, but between TupleJump and DataStax, have you seen any performance differences?
Yeah, I'm not that familiar with the libraries, but yeah, we can certainly talk more afterwards. So to be clear, these are examples of things that people have proposed. This is actually, all four of these, I think, are not from Databricks, actually. These are other people in the community, and we're kind of pushing them all to use the external data source API so we can have one kind of clean way of interacting with all of these. And so, like I said, the nice thing here is we're trying to support data source specific optimizations, including reading unneeded columns, also pushing predicates down to the data sources. If you want to see an early preview of this API, it's up on GitHub and this pull request. And we'll be merging this in before Spark 1.2. That's kind of the goal, is to have this API be one of the new features in Spark 1.2. And I will tweet these slides at some point. I didn't manage to get them into PDF form, but on Twitter if you want to see them, or we'll probably put them on the Databricks blog at some point as well. So I want to give you a quick preview of what this API looks like, and then we're actually going to dive in and do a little bit more coding before wrapping up. So it's pretty simple, actually. If you want to define a new data type, there are two. You need to define a new type of base relation. This is this top class here. And base relation has to have a SQL context, mostly for bookkeeping reasons. And it also has to have a schema, which is represented as a struct type. So a struct type is a collection of columns with names and data types. And as long as you can define that, you can define a new data source. So this could be something that you get from Cassandra. This could be something that you infer from the metadata on an Avro file. This could be something that the user gives you. But basically, the idea is that you specify the schema. And then you have to specify how to actually get the data. So there's a couple of different traits which allow you to specify how to get the data. The simplest one is table scan. And a table scan just returns an RDD of rows for all of the data in this data source. And then all of the rest of the processing will happen with Spark SQL. If you can do things like eliminate unneeded columns, you can do a prune scan, and then we'll tell you which columns we want. And you could also do a filtered scan, where we tell you which columns you want, and we give you the opportunity to look at all of the predicates that are being applied to you and decide if you can handle any of them. And you can actually pick which predicates you can apply. So if you can't do, like for example, you probably can't evaluate arbitrary UDFs, but you could do equality predicates. You can kind of look through them, find the ones you can handle, pass the other ones back to Spark, and then we'll let you kind of push those into your underlying data source. So I want to do a real quick example where I show you how you could actually do this for Avro. So I wrote a whole bunch of boilerplate. It's not super important to understand the boilerplate, but I'll walk through it real quickly. This is kind of basically what I did was I Googled Avro Spark, and I took all of the examples from the internet and copied them here. So at the top here, I've got a function that I think the schema. It takes in a location. It creates a reader, and then it basically converts the Avro schema. So Avro is this self-describing data format where you can ask it what the names of the columns are and the data types, and it basically does this conversion. So you give it an Avro file, it does the mapping, an Avro int is a Spark SQL int, an Avro record is a Spark SQL struct, etc. So whatever mappings make sense for your data source. So that's one function that we've got. And then we've also got Avro RDD, which takes in an Avro file and returns it as an RDD of Avro records. And then we've got convert to row, which takes an Avro record and a schema and converts it into a Spark SQL row. So let's actually build a data source. So we're going to start by defining a case class. All tree nodes need to be case classes in order to make all of our reflection magic work. We'll call it Avro relation, and it'll take in the location of the data and a SQL context. So we'll do SQL context. And cool. And I want this to extend base relation. So this is that class that I talked about before that is basically the base class for any new data source in Spark SQL. So it's telling me I'm missing my two members. So I need to define the schema. So I'll do val schema equals, and I need get schema. So we'll call our helper function from above with the location. And we'll turn this into a val. And so now we've got an Avro relation. So now we've got a data source that Spark SQL can understand. And so I could construct these by hand, but we probably want something that's a little closer to what the existing data sources are like, where you can say SQL context.parquet file or SQL context.json file. So we'll do a little bit of Scala magic. Implicit class Avro file. So we're going to define something that basically, this is a library extending technique in Scala. SQL context. And so we're going to basically add a method to SQL context after the fact. We'll call it Avro file. It'll take a location, which is a string. And it's going to construct an Avro relation, which takes a location and a SQL context. And we'll make it a schema RDD. So now I've got this Avro file method. So I can actually do SQL context.avro file, and we'll get episodes.avro. So we've got one error, but you can see this actually worked. We've kind of, well, at least part of the way through, we've read this in, and if I pull up the query execution, and I look at the analyzed plan, you can see it actually did figure out the schema of this thing. So I asked it for its output, and it gave me the title and the air date. I could also do something like, I guess I could do .print schema. See that in a slightly nicer form. So we got a title, an air date, and a doctor, just string, a string, and an integer. But if I actually try to run this, I'm going to get an error. So it's saying, basically, there's no way to run this. There's no plan for doing this. So what I need to do is I need to tell it how to actually retrieve the data. So we'll say with table scan. So we're going to implement the table scan, because it's probably the best choice for Avro. We have to implement build scan then. And this should do Avro RDD. And we'll pass it the location. And then we need to convert these to rows. So map convert. What did I call that? Convert to row, which takes the schema. Ta-da! So we have now added support to Spark SQL for reading Avro, and I can make this a little bit easier for you to read. Register temp table. Ta-da! So, and you can actually do things like figure out who the most popular doctor is, I think, maybe even. So if we do, I'm not sure if this is going to work. I probably should have practiced this. No, that's not going to work. You need data that you can actually graph. Sorry, there was a question?
Is it like Spark SQL?
So no, so the graphing is actually, this is Databricks Cloud. But all Databricks Cloud is doing is taking a schema RDD and using some JavaScript to plot it. So basically, what you're seeing is schema RDDs for the most part. So that was adding a data source. So now that you've kind of learned about SQL, you've learned how to write rules, you've learned how to add data sources to Spark SQL, how do you actually contribute to Spark? So I'll go through this pretty quickly because we're just about out of time. But basically, if you're a Spark user already, pick a bug or a feature that you'd like to have. One thing I kind of want to mention here is we do all of our kind of coordination through Jira. So basically, all of the decisions that are made by anybody who's working on Spark go on the Jira. And in fact, we also tag things that we think are great starter projects so people can find them easily. So search for this starter tag here, which is something you can look for. And basically, those are a bunch of projects we think would be great for people just getting started. Another thing is people often ask me, like, what's going in release? You can actually get all of that information from Jira as well. If you just set the target version to 1.2.0, you can find out what at least I think is going to go into the next release. So that's kind of a great way to really keep your hand on the pulse of the Spark project, is kind of by watching the pull requests and watching the Jira. Kind of another thing is, now I've picked a project to work on, what do I actually do? So it's pretty simple. We do all of our collaboration through GitHub. So just fork the Spark project on GitHub. Make sure to comment on the Jira or create a Jira to say you're getting started on it so we don't have duplicated effort, people working on the same thing. Write the code. Push your code to your branch or your fork of Spark, and it'll give you this nice green button. All you have to do is click create pull request, and that'll notify us, and we'll comment on it and then merge it in. Another question I get a lot is what makes a good PR? How can I make my PR get merged as quickly as possible? So some quick tips here. So one is follow the style guide. When you've got hundreds of people contributing to a project, it's very important that we have kind of a unified style so you can and read it quickly without having too much cognitive overhead. You can even check this locally by running spt Scala style. Other details, add tests for anything you change. Basically that's the first thing I look for in any PR. And almost any time I say add tests and they add tests, they find a bug. So it's a good forcing function to keep saying that. Another thing is shorter is better. Like we love to get lots of commits, but the shorter your commit is, the faster I can understand it, the quicker I can reason about how correct it is, and the faster I merge it in. So when I get like 10-line bug fixes, I merge those in immediately. When there's 1,000-line refactorings, those are much harder. So pick ambitious things to work on and break them into small segments, and it makes everybody's life much easier. And then finally, label your pull requests, put the JIRA on them, tag things with SQL or Core or PySpark or whichever part you're contributing to. Basically, I do a filter, and I look for all of the things that are tagged SQL, and I review those. So if you forget to do that, you have to wait until somebody else tells me to look at it. So that's my talk. Are there any questions? Yes?
I was looking at the front page. I was expecting to see how you're better than Hive, but I wasn't able to find it.
Well, sorry, we'll try to brag more. Yeah, so the question was, there doesn't seem to be much of a comparison to us and Hive on our web page. So I would say that in general, in most of the benchmarks that we've run, we actually just did a pretty complete run of TPCDS with a variety of queries there. We are substantially faster than Hive, even Hive 13 with TES. So that's certainly not true for all queries, but I would say speed is definitely a case where we're kind of keeping the Spark tradition of being much faster than MapReduce systems, and at least in our experience, even kind of systems based on top of TES. I would say looking at performance though is really missing kind of one of the coolest parts, which is the integration with the rest of the Spark ecosystem. When you've got Hive, you've got just SQL. And I think this can be said for many different databases. With Spark, you can read from any data source that Spark can read from. You can even do ETL in Spark code and then immediately switch to running SQL jobs on it. You can integrate with MLlib and kind of other APIs like that. So I think really the richness of the data you can work with, the ease at which you can write functions, so like Lambda functions are another great example. Writing a Hive UDF is like 50 to 100 lines of code. You have to compile a jar. You have to upload it to your system. If I wanted to write a UDF in Spark SQL, I would do register function. Let's do like string length, right? So I can do this. UDF written. So, and now you could use that in SQL queries. So I think like really, speed is great, and Spark SQL is really fast, but we also have, I think, significantly richer APIs and integration with the rest of the Spark ecosystem. Other questions? Yes?
You recommended that one use Hive context, and yet your examples use SQL context. That's an interesting point. It's a Hive context. It's just, I call it, and in fact, one of the big pushes of the 1.2 external data APIs is to remove this divide. So everybody just uses a SQL context, and you register different data sources with it. We're not there yet, but the SQL context I was using was actually a Hive context throughout. You should always use a Hive context. And I hope that in Spark 1.3 or Spark 1.4, you will always be able to use a SQL context functionality of any of the data sources without having to worry about libraries. Unfortunately, we haven't had enough time to really disentangle the APIs enough to make that possible. But that's where we're heading. And towards that end, at least in Databricks Cloud, we call everything SQL context because that's the direction we're going in. Any other questions? Yes?
Register temp table. What does that mean exactly? How temp is temp?
It's very temp. It is, you should think of it as temporary as the RDD that you registered it on. It lives only for the life of that SQL context. So just like RDDs, when the JVM shuts down, it's gone. If you want to persist it, I recommend using save as Parquet file or save as table, which is only available on Hive contexts. But basically what that will do is that will create a persistent version of it. So, and then you can register those in. We are also looking at extending that so that it would be possible to kind of interact. So basically right now, save as table is not super powerful. It always saves using the Hive default SERDI. What I would love, and kind of the goal for maybe 1.2, maybe 1.3, is save as table will also take the storage format you want. And so then you can have something that looks like persistent tables where you can pick arbitrary storage formats. That's coming someday. Other questions? Yes?
Do you have any kits that have to do like a Kickstarter and the Internet of Things solution that can be integrated easily with Spark platform? I mean, this is really way out, but I'm just wondering if there could be some documentation to help Internet of Things project get off the ground.
That is a good question. I am not super familiar with the Internet of Things, but I would love to talk more about it afterwards. Any other questions?
How much integration have you done with Parquet stack for like filter push down?
Not yet, but that's like a top priority. So we have one of our employees at Databricks is like tasked with looking at that and integrating that. So if you know a lot about it, I would love to talk to you more, because I don't really know what's available, but I think that's really, I think we in terms of storage formats, we have put the most effort into Parquet so far, and that's kind of where we see ourselves continuing to put the engineering effort. Like, I would like to support all data formats, but when I have engineering resources to devote, I'm devoting them to Parquet now. Yeah, I'll let you first. So there's not an official way to do this. Because you can do arbitrary RDD operations inside of streaming jobs using the transform operator, you kind of can do this. But like, really, if you want, like, if you say streaming SQL to me, I'm going to expect things like window functions and stuff, and none of that is going to work at this point. There are projects that have kind of done prototypes of this, but there's no production-ready implementation of that. Not the near-term roadmap. I mean, it's definitely something I would like to do, but it's not like planned for 1.2 or 1.3. And you had a question.
Can you elaborate on that Parquet? Like, it seems like Databricks is kind of about it a lot. I suppose you don't talk about RC file and ORC file.
I mean, that is mostly an artifact of the fact that it is the fastest way to load data into Spark SQL at this moment. That said, there is a pull request open right now for adding native support for ORC files to Spark SQL, kind of as an equivalent first-class citizen to ORC. So I wouldn't say that this is like us taking a side in a religious war of data formats. Of limited engineering resources, and I want at least one very fast data format in Spark SQL. So the effort so far has gone into Parquet, but the community is putting effort into ORC, so I think that should work as well in Spark SQL, and that is something that is important to us at Databricks. Yes?
So two questions. First, how will you compare with the Python project by Novella?
So so I mean, so Databricks is also somewhat affiliated, and we're doing quite a bit of work inside of Spark to make it possible for the Hive on Spark project to kind of have the APIs it needs to plug in. I think a good way to look at this is if you have an application that depends on, that you really want to do absolutely no porting effort, you want a complete drop-in replacement for Hive, including all of Hive's quirks. Hive on Spark is a great drop-in replacement, and because it's running on Spark, I anticipate that it will run very quickly and fast. We, for example, have no interest in mirroring every semantic Hive has. So there is a flag in Hive that says, "Give me the wrong answer to outer joins," and we're not going to mimic that. So if you want those sorts of things, Hive on Spark is great. I think that in general, Spark SQL is going to be more tightly coupled with the Spark project, and I think there are optimization benefits to be had there. But really, I think they're both great projects.
Is there a wrong way to use Spark SQL?
A wrong way to use Spark. Oh man, that's like a whole talk in itself. Well, there are a couple of wrong ways now, but actually we're trying to fix them in 1.2. Let me give you an example of something that you should not do in 1.1, but that you can do in master 1.2, and that's called .cache on a schema RDD. And so that's kind of weird, right? You'd think these are normal RDDs, right? I can do everything I can normally do on them. And the reason for that is in Spark 1.0 and Spark 1.1, cache table and .cache are two different operations. When you call cache table, we do the very efficient in-memory columnar format. When you do .cache, we do Spark's keep all of these objects alive in the JVM way of things. So it is significantly harder on the garbage collector, and in many workloads where the columnar caching performs great, we see standard caching just completely tip over with GC problems. So what you need to do is you need to say .cache, .register temp table, cache table, and then pull that table out and work on that. And you get kind of all of the benefits of the columnar caching, with an RDD that you can do normal RDD operations on. We fixed that because it was really confusing and people were mixing it up all the time. Now when you do .cache, it always uses the columnar caching. It even does things like if you say Parquet file .cache, and then you create a new Parquet file that references the same set of Parquet data, it's doing logical plan matching, unlike the rest of Spark. And so it will realize these two are the same files, I should just use this cached version.
Do you recommend tracking in 1.1 branch or wait for patch releases?
So we do, so yeah, I would definitely, I think tracking 1.1 is pretty safe. We're pretty careful about what we port back to it. I run on master, and I actually run into surprisingly few problems. I wouldn't recommend that for like super production, but like for development, we're pretty careful. That said, run your production stuff on good releases. Maybe Matei has thoughts on this. He's raising his hand.
I was going to ask, can you talk about analytics?
Oh, okay. Yeah, that's a very good, thank you. Good question. So another kind of thing about Spark SQL, in schema RDDs, is they're very similar to what you see in something like a pandas data frame, right? You've got this collection of data. We've got names, we've got columns, we've got rows. We can kind of slice and dice it in arbitrary ways. And another cool thing that we're working on for Spark 1.2, kind of on the MLlib side of things, is making schema RDDs the kind of unified data format for working your pipeline. So I've got some data, I want to do some transformations on it, I want to regularize it, and then I want to feed that into a machine learning algorithm. I want to split it up into a test set and a training set and run on the test set. And so kind of viewing schema RDDs as data frames and through MLlib is kind of another one of, I think, the big focuses of.
Yeah. Pros and cons of Arcade data format or hard column control versus like edge-based. Do you think they are in feature parity, or when do they become?
No, I think these are actually quite different use cases. I mean, Parquet is for data at rest that is not, it's very difficult to update, right? Because you have to kind of re-encode the entire Parquet buffer in order to do it. It's like data at rest where it's relatively wide and you want to read some small fragment of it often. Like doing a select star on a Parquet file doesn't make much sense. And if that's what you're going to be doing all the time, you should probably be using Avro instead of Parquet, although there are possibly still columnar compression reasons. HBase, I would say, is for data where you want to do point mutations within it. Kind of relatively often. It's going to be much more efficient for that sort of workload. Yes?
So does Spark SQL have the same update issues as with the Hive, or are you better than them?
Can you explain what you mean by update issues?
Let's say, somewhere I read Spark SQL, they want to have ANSI SQL 92.
Got it. Yeah, so we do not support the update command as of now. Something we would maybe consider working on. Update, so really, my view on this is Spark SQL, at least in its current incarnation and kind of where the direction we're pushing it at the moment, is more for OLAP analytic type workloads. And in that case, it's mostly immutable data, and so updates aren't a big part of it. So that's not going to be an immediate focus. I won't rule it out in the long term. And maybe we'll take like one more question so we don't go too long, and I will stick around to answer as many questions as people want. Is there anything else? Or is that too much pressure? Okay, yeah, last question.
What's your opinion on Optic?
What's that? Optique. Oh, yeah. So I mean, Optique. So for those of you who aren't familiar, the question is, what's my view on Optique? I think Optique has very similar goals to Spark SQL. I think it's actually a pretty cool system. We looked at Optique significantly before diving into Spark SQL. The idea of building an optimizer as a modular collection of rules has been around the database literature for many years, and I think it's great that they went down that path. The things that I like about Spark SQL, I am a Scala fanatic, and I think you can write prettier, simpler Scala code than Java code any day. So I don't know, look at the rules and do a comparison and decide which is your taste. OK, thank you very much.
Great job.
Thank you.
Very
Thank you very
excited.
much.
Well, thanks a lot for that. This is perfect. I was